Hi, I'm Daniel Abadi. I'm a professor at the University of Maryland in College Park. And I'm here to talk about today some trade-offs in distributed systems, and particularly the consistency versus throughput trade-off when dealing with database systems. So that's what we're going to talk about today. So in general, when we deal with distributed systems, there are lots of trade-offs to consider. I mean, there's no free lunch. And then any decision you make, you want to optimize for one thing, you often have to give something else up, right? So for example, some well-known options. The CAP theorem has been around for around, I don't know, 15 to 20 years or so by now. It's very famous. It's explained very clearly that if you want to have a consistent version of the data across all replicas, wherever they may be in the world, it doesn't come for free. You have to give up some availability, right? So it's possible that your system may be unavailable for writes, or even sometimes for reads as well, if you want to have a fully consistent system. Right? That's the CAP theorem. That's well known. Another example is the PACELC theorem that says that not only do you have to trade off availability for consistency, but also in the common case, you also have to trade off latency for consistency as well. Right? So if you want a fully consistent system, you have to pay for some amount of replication. That takes time, and that causes an increase in latency in the system. Right? So these two are sort of fairly well known and well agreed upon. If you want consistency, it's important. You get three things. You get sort of a system of which it's much easier to develop to write application programs over it, but you do have to give up some availability and you give up some latency. And the question I want to discuss today is: do you also have to give up throughput as well for consistency, or is it really not the case that there's a trade-off here? And it's an interesting question, and it's less obvious than you may think. And so we'll go into that now. So let's go into some background first, right? So before we get to distributed systems, and particularly distributed database systems, let's talk about a single node, regular old-fashioned database system, right? So we're a simple application where we have two tables in the database. One is a table indicating the things that we're selling. Let's say, for example, we're a retail application, right? So we're selling things and widgets, and we have customers, and so one table indicates what are the price of the current stock inventory that we're currently selling and how much is left in stock. And then we have some information on our customers, in particular, how much store credit they may have to be able to buy items in our database system, in our retail application. So two typical tables, and a typical transaction we want to run is a customer may want to buy something using store credit. Right? So for example, let's say the customer 2 comes along, who currently has a store credit of 100 and wants to buy widget 3, which currently has a price of 79 with a store credit. So how do you do this? Originally, what you would do is in a single system, before we get to distributed systems, in a single system, what you would do is you would read the relevant data, right? So in this case, we're going to read the widgets table to get the item that the customer wants to buy, and we have to read the customers table to get the value of the credit the customer has to be able to buy the item, right? So in order to do that, there's different ways to implement this, but the traditional, most common way to deal with this is to lock both things you're going to read. That way you don't have to worry about other writes coming along and interfering with what we're trying to do and potentially causing isolation problems, right? So we'll lock widget 3, which is what we're trying to read right now, and we'll lock also customer 2, which we're also trying to read right now. And then once they're both locked, we can run the transaction, right? So first we have to check to see how much stock is left, right? So if we don't have anything in stock, we should abort the transaction. We can't run this purchase. And right now we're fine. We have exactly one left, so we're fine. And similarly, if you don't have enough credit, right? If the store credit of customer 2 is smaller than the price, then there would also be a problem we should abort. But in this case, also we're fine because we have 179, so that's also fine. But if either of these two things were false, then we'd have to abort the transaction. Since they're both true, sorry, since we both have enough stock and we have both enough credit, then we proceed with the transaction and we decrement the stock, right? So we make the purchase, so therefore stock will go from 1 down to 0, and the credit will go down from 100 down to 21 as we subtract the price from the store credit, right? And then we can release the locks and we're done with the transaction, right? So in a single node system, this database transaction is fairly straightforward to run. Just requires a little bit of locking, but we're going to get a correct result when we do this locking. And certainly there's no concern about any of the ASP properties here. Will guarantee atomicity and consistency, isolation, and durability. So that's great. But now what happens if we have a distributed database system, right? So it turns out that this very simple transaction becomes much harder once you have the data divided across multiple different machines, right? So here, here we have the same exact two tables, the widget table and the customer table, and customers are buying widgets. So we have sort of one widget per node and two customers per node. That's a simple division, a simple partitioning of the original customer table and the original widget table. And now what we want to do, let's kind of get rid of the two which we don't care about, because we're only focused still on customer 2 buying widget 3. So I just got rid of the two partitions which are not relevant to this particular transaction. Now we're showing here on the screen just the two which are relevant, which is the bottom left, we have the widget 3, which is what we're trying to buy, and on the top right we have the customer 2, which is trying to buy that widget. Right? So we have now two machines storing data relevant to the transaction. So in this case now, what do we do, right? So the original step can be the same. We can still use locking if we want. Not all distributed systems uses locking. You can end up with some distributed deadlock problem, which can be an issue. But that's just keeping it simple and assume we're using locking. So we'll go ahead and we'll lock the two relevant tuples in a database, right? So the bottom left machine will lock widget 3, and the top right machine will lock customer 2, which were indicated by the first two lines of our transaction here, right? We did a read of W and the read of C that caused these two things to be locked. Okay, fine. And now the next step in our transaction to check the stock if it's less than 1 or not, this is also fine. We can do this entirely on the bottom left machine, right? To check to see if stock is less than 1, you just have to have that code can be run entirely on the bottom left machine. And if it's less than 1, then we'll abort. And if it's 1 or more, then we won't abort. So that's fine. However, the next statement is a little bit harder to run, right? So here, we want to check to see, is the store credit less than the price, right? If so, we need to abort, right? But the problem is that the c.store credit is stored on the top right machine, and w.price is on the bottom left machine, right? So we have two different machines storing data relevant for this to run this if statement, right? So there has to be some communication across these nodes in order to be able to run this if statement, right? So there's two ways you can do this. Let's just do one of the ways, right? So we'll have the bottom left machine send the current price after locking the data item to the top right machine. And so now the top right machine can now do the whole if statement, right? Now it has the price and it has the store credit. So it can check to see is the credit less than the price. If it is, it'll abort, otherwise it'll continue. Right, so at this point, the bottom left machine did not abort because the stock was enough. The top right machine did not abort because the store credit was enough. So now we can go forward with the last two lines of the transaction. We can subtract 1 from the stock and subtract the price from the credit, right? So here we are on the bottom left. The stock is now 0, and the top right, the store credit is now 21, like we had before, right? So these lines of code are done separately on each machine. So far, so good. But now the problem is that each machine does not know if the other machine aborted or not. They don't know if they were able to succeed with their responsibilities for the transaction. So we have to generally run, when we're done doing all the work of transaction, we generally have to run a commit protocol to be able to communicate each machine with each other to explain sort of whether they were able to do their part of the transaction. And if so, we can commit, otherwise we'll abort. And the most common protocol is what's called the two-phase commit protocol. And the way this works, it's sort of like a 2 rounds of communication to ensure full durability and atomicity, where one machine initiates the protocol, so let's say it's the top right machine, so they tell the other machine to prepare the protocol, and then the other machine then responds back whether they were able to commit the transaction, at least locally. If so, they can say they're ready. If not, they'll say they wanted to abort. And then the top right machine will then gather responses from every machine involved. Here it's just two machines, and then come up with a final decision. Here it's commit. And then we'll indicate that the bottom right machine will then say, okay, I got your commit message, we're done now. And now at this point, the transaction may commit. So it's 2 rounds of communication, in addition to the round of communication before the commit protocol. And the key thing to note here is that while this protocol is running, we have the relevant data locked, right? So the widget 3 and customer 2 was locked throughout this whole transaction. We locked it at the beginning when we did the read. And we kept it locked not only during the transaction itself, but even during the commit protocol after the transaction, we kept it locked. And this could cause a throughput problem, right? So if there are other transactions which conflict with customer 2 or widget 3, i.e., they want to access either read or write customer 2 or widget 3, then they have to wait because these records are locked. The other transaction will have to wait for the locks to be released. And so when you have lots of conflicting transactions all trying to access the same data, you hold locks for too long, it's going to cause a general throughput reduction in the system. And so here it would seem that this problem, we never had a commit protocol in a single node system we saw before. There was no communication, there was no commit protocol, so there was no holding of locks during communication, right? So all of a sudden, by moving to a distributed system, all of a sudden we end up holding locks during communication, and that's slow, and that can potentially cause a throughput reduction. Okay, but that's just to commit the transaction itself. But what if we have data replication? And this is, almost every distributed system will replicate data because you want to have high availability. So and good performance and lots of read performance at least, and you want to have durability. All these, there's lots of reasons to replicate data. Right? So pretty much every distributed system will replicate data across different sets of replicas. And the problem is, if we're doing replication in a consistent fashion, such that each replica is guaranteed to see the same data at any point in time, then you end up having to hold locks during replication. Roughly speaking, again, there's some exceptions, we'll get to those soon, but roughly speaking, you have to hold locks during replication, right? So what happens is we first do the transaction on one replica first, right? So here on the left side of the screen, we have the final result of this transaction with store code as 21 and in stock as 0 after running two-phase commit, right? So basically this slide picks up where the previous slide left off, right? So first did the communication, then we ran two-phase commit, and now we are the left side of the system, left replica is done with the transaction. But before it commits now, it wants to replicate the results of the transaction because the right replica still has the old values, right? It still has a store code of 100 for customer 2 and in stock of 1 for widget 3. So it has all values still, right? So before we commit, we want to make sure that all replicas agreeing with each other before we release the lock, so that way we can sort of tell the user once we commit, we can tell the user that no matter where you read, everyone will see the same value, right? Whether it's replica 1, replica 2, either way, everyone sees the same value, right? So how do we do this? Right? So while holding locks, we replicate the data. We perform the changes that replica 1 did on replica 2. There we go. Now we have a change of 21.0. And then we respond back that we're done. And only at that point can then replica 1 now commit the transaction, right? So after two-phase commit and after application, only then can we release the locks, right? So here we have another set of period of time where conflicting transactions cannot run. And this is typically even worse, right? Because typically speaking, you're running two-phase commit within a region, a single region, right? Just one replica is typically in one region. And so you run two-phase commit within that one region. But now, if you have a truly global system, a global deployment, and we're running application across replicas, now you have a major latency delay to do this replication across geographical distances. Like, for example, it takes around 200 milliseconds or so to go across the world, and then back again, there's even more. So it's very slow latency-wise, and that's the PACELC theorem. But here we're seeing also a throughput issue as well, right? Because since we're holding locks during replication, no conflicting transactions can run while we're doing the application. So if we have other transactions which want to access customer 2 or widget 3, they can't run, they'll get delayed. And if you have lots of conflicting transactions, you'll see an overall throughput reduction as the system gets clogged up with too many waiting transactions. So to summarize, we saw sort of two potential problems when by switching to a single system into a single node system to a distributed system. We saw two problems that come up, right? So number one, we saw that that the latency will decrease. Actually, will increase. We'll have it'll take longer to run the transaction, but by going from a single node to a multi-node deployment, latency increases for two reasons, right? Number one, because we have to run a commit protocol to make sure we can commit, and we need that commit protocol if we're guaranteeing atomicity, consistency, and durability of acid. Then you need a commit protocol. You can't get away without it. So therefore, that takes time. So that costs you latency. And we saw also by holding locks during the protocol also costs you in throughput as well. Similarly, by and a second problem that comes up is by replication, right? We saw that when you hold locks during replication, you end up needing to increase latency as you wait for the replication to occur while holding locks. And since you're holding locks, then that can cause a throughput reduction as well, right? So both because of replication and because of the commit protocol, you end up having latency increase and throughput reduction. right? So that's that's the problem. And so this whole discussion was assuming we're using a locking protocol, and that's fine. That's sort of one way where this come up. But the truth is even if you're not using a locking protocol, if you're using optimistic protocol or multi-version protocol, it's still the case that you cannot allow conflicting transactions to run while we're doing two-phase commit and while we're doing replication, because if you do, you may end up having some major correctness issues in terms of the application. So although the example we saw was locking, this is also true for optimistic protocols, and it's also true for multi-version protocols as well. Okay, so that's the case. Then I've basically been saying that that we have two problems, right? So we have both a transaction throughput problem and also a transaction latency problem by having two-phase commit and having replication. So why is it the case then? So that the PACELC theorem only talks about latency and not throughput, right? So it would seem that, just to quickly review PACELC theorem, right? So it says that when there's a partition, you have to trade off between the test atomicity and consistency. But if there's no partition, or just a regular baseline case, just run transactions the way they're supposed to run, then either you guarantee consistency and every application can see the same value, in which case you have to pay the latency to get the replication to get every replica to agree, or you pay consistency. You reduce consistency, you get better latency that way, but then now your replicas are not agreeing with each other, right? So that's the PACELC theorem. Clearly indicates a latency versus consistency trade-off. So what about throughput? It would seem that there should be a throughput trade-off as well, based on the arguments we've been making so far. So the truth is that it's not the throughput trade-off is not as fundamental as latency as the latency trade-off. So and the reason is that no matter what you do, and no matter what your workload looks like, you will always have a latency trade-off, right? So as long as you need to have every replica agreeing on the values of the state of the database system, it just takes time to get that data across to all the replicas, right? So either you send all data to the same replica, in which case then you have other issues, around availability and other things, or you have to spend the latency cost to make sure that all the replicas are agreeing with each other. So and this is true no matter what you're accessing, right? So even if you have no conflicting transactions, and every transaction is touching something else, still, because we don't know for sure that they won't conflict in advance, you have to still hold locks and perform the application, and then not commit the transaction until the application is done, right? So when you're doing synchronous application and you don't commit until the application is done, whether it's conflicting transactions or not, you still have a latency cost. However, when it comes to throughput, it's not the case, right? So we only had all the throughput problems we saw was from holding locks or otherwise preventing conflicting transactions from running while performing two-phase commit and replication. If there are no conflicting transactions, then we're fine. There actually is no throughput reduction, right? So it's the only problem is just we're only preventing conflicting transactions from running. So if you have other transactions which you can run, which are not conflicting, then it'll be fine from a throughput perspective. So that's one point. The other point is that you can just not guarantee strong isolation, right? So if you run transactions in such a way that it's okay if we have two conflicting transactions running at the same time, which may sort of interfere with each other. If your application is designed in a way such that doesn't matter, and therefore you can reduce the strong isolation guarantee from the system, then you don't need to hold locks while you do application. You don't have to hold locks when you do two-phase commit, and therefore, again, you have no throughput trade-off. Furthermore, the third point is that there's a whole other sort of set of systems called deterministic systems, which are well beyond the scope of this talk. And I think we're running low on time at this point, but they work in such a way that they actually run two-phase commit and replication outside of transactional boundaries. In other words, they do the replication before the transaction even begins, so they don't have to hold locks during replication, and also they actually get rid of most of two-phase commit. So basically, so in short, they also get rid of the throughput trade-off entirely, even if there are conflicting transactions. So in short, either there are no conflicting transactions, or we don't care about strong isolation, or we use a system. All those things, then the throughput trade-off is there's no throughput problem, and that's why it's not the same level of the latency trade-off. So in practice, I guess the main take-home message here is, in practice, Usually there is a throughput trade-off, right? So most of the time, if you want consistency, you're going to pay throughput as well. But it's not as fundamental, and therefore it's not part of the PACELC theorem. It's a little bit less of a fundamental trade-off. So that's the end of the talk. But please feel free to contact me if you have any questions, either during the session or afterwards. My contact information is on this slide, I'm very passionate about distributed systems and happy to talk to people about them.